All right. So for those of you, has anybody noticed a problem with Excel homework number 2?
Yeah.
Yeah. So why? So someone just brought it up to me today. So I created, or I uploaded it originally in another section. And I copy and pasted it over yours because it's the same assignment, right? It's the same 2 different stats courses, different sections, or same stats course, different section. And apparently the links never copied over. So it's been sitting there without any links, without any a Word document for instructions. So I was just made aware of this. So I uploaded them this morning. So now when you click on that assignment, you should see the Word document kind of outlining the questions, and then the data set is kind of that Excel file. So I don't love doing this because I don't really want people working on it kind of up to the exam date. The due date was set as next Wednesday. So I'll push that to the exam date. I don't suggest waiting till the exam day to then do that Excel assignment. But because those files are up there, I will kind of extend that. So try to start working through that Excel assignment. After today, we'll cover everything you need to do anything on the Connect or Excel. So just try to start wrapping those up so you can start taking a look at the practice exams next week as we kind of work through those a little bit on Monday and Wednesday. Kind of preparing us for that exam. Okay. Any other questions for me before we go? The other thing I wanted to mention is after I'll probably get it posted when I'm done teaching my block of classes. So this afternoon, I will put up one of those videos that kind of introduce the idea of what we're going to talk about in next class. I kind of expect you to watch that before Friday. It's like 3-4 minutes long. Kind of introduces the final thing that we'll talk about before we kind of head into this exam, which is what we talk about on Friday. Okay. Other than that, you can pick up where we left off. Right. So we were talking about these discrete random variables, right? So we have some experiment. We don't know what the outcome is going to be, but we know that the different probabilities of seeing these different outcomes, right? There's varying probabilities. So once we look at these outcomes and their associated probabilities, we said we could come up with a mean or expected value. So this was very similar to a weighted mean, but without the denominator, because our weights were probabilities. So the sum of our weights, right, will always be 1. So the same kind of idea holds for the variance. It's just like a weighted variance, but without that denominator, because the sum of our weights, some of the probabilities across every possible outcome should always add to 1. This is the idea of, if we had this data set with a number of new hires and we have 0 through 12 and all their associated probabilities, we go through the very first outcome we can see of 0, subtract that mean of 5.14 we found that last class, square that deviation from the mean, and then how likely do we see that deviation from the mean? Well, the likelihood we see 0 occur is a probability of 0. Right? That one, when we multiply by its probability, essentially doesn't influence the mean at all. Or sorry, doesn't influence the variance at all, which makes sense, right? It has no likelihood of occurring, so we shouldn't be adding anything to the variance. Then go to the next observation, next outcome, which is 1, subtract that mean of 5.14, square the deviation, then multiply that by the probability we see 1, which is 0.06. I continue to do this for every observation, add them all up. We don't have to worry about the denominator here because the sum of our weights is 1. So, we had, I think last class, we found the mean of this data set was 4.2. What I'm going to do to go through and find the variance, right, is just take every outcome. And I think I delete the, oh, there you go. So we've got that mean of 4.2. So we'll look at the first X outcome, right, which is 10. Subtract that mean, square that deviation from the mean. And then what's the probability we see 10 occur? Times 0.15. Right, that's our weight. We then add to that the next value minus the mean squared. What's the probability we see 6 occur? 0.25. Basically, just go through the rest of these. Well, the probability we see 3 is 0.4. And the probability we see 0 is 0.2. So it's really the same process we've been using to kind of find a weighted variance. right? Take that deviation, square it, and then multiply it by the weight here. That's the probability that we see that outcome occur. Okay. So which of these right away should I be able to rule out as a possible answer? I mean, one of these things don't look like the others. I was guessing probably this one, right? So why can't I see negative 66 be the variance? Everything's being squared, right? Our variance is kind of starting at 0, right? Think about it kind of like probabilities. The lowest probability that something can occur is 0. It just can't happen. The lowest variation we can see in our data set is no variation, 0. And then from there, it just goes up, right? The lowest it can be is 0. And then from there, just a higher and higher variance, so a larger and larger positive value. So we can never see a negative value for our variance. And if the standard deviation is just the square root of the variance, we could never see a negative value for our standard deviation. So if we go through and compute this, I believe that 9.96, right? If you enter this into your calculator, I have up here on the board, went up with 9.96. So not wildly different from things we've already done. Any questions on this? I had to grab some stuff we talked about last class and going back, but I want to kind of finish that. I'll try to end on this because I think it's kind of fun. So we'll come back to this because I want to introduce one of the two very specific discrete random variables we'll talk about kind of to end out this week. Okay? So the first one's going to be this binomial distribution. So in order for us to know that a discrete random variable is binomial, a couple of things have to be true about the situation we're looking at. Okay? So we have to have some experiment that we're literally running in the exact same way over and over. This could be as simple as flipping a coin. Right? But I'm flipping a coin, recording the result. Flipping a coin, recording the result. I'm running this experiment over and over, just flipping the coin the same way every single time. So we'll call that number of trials, that number of times I flip the coin, N. Okay? We have to have only 2 outcomes. So we'll say like success, failure, but really this is just like, it could be heads, tails, right? And the success is whatever I'm interested in finding the probability of, right? So this could be something like the number of car crashes on a road. Well, that's my success. There's a crash, and my failure if there's not. It's kind of weird. So, don't think so much success is a good thing. It's just, what are we looking for the probability of occurring, right? The thing that we're interested in occurring, that's our success. Okay? We also need the probability of success in any one trial to be the same. Okay, so this is the idea. If I flip a coin, the probability that comes up heads is every single time 0.5. And then we need our trials to be independent, so that if I get a head on the first flip, it doesn't change the probability I get a heads on the next coin flip. Right? So coin flip is like the easiest example to think of that fits the binomial distribution. Right? We'll kind of have some other examples as we work through this today. Okay. So, I'm never trying to trick you on these. A lot of times, like on the exams, especially with the practice exam, I'm not asking you to identify necessarily what is a binomial distribution, but kind of the setup of, are there 2 outcomes? I've got this number of trials and kind of the highest possible number of heads I could get if I flip a coin 100 times is 100. Right? I'm kind of capped, right? We'll start to recognize these as we work through the example. So, what we might be interested then is, okay, out of these 100 coin flips, what's the probability that 60 of them are heads? Out of these 100 coin flips, what's the probability all 100 come up heads, right? So I can find the probability of different number of successes, right? 1 out of 100, 50 out of 100, 30 out of 100, right? Whatever it is that I'm interested in. So whatever this number of successes we're interested in, we're going to call that X, right? Or think about this differently. What's the probability that this random variable, which we said we kind of use capital X to represent, is equal to all the different possible outcomes we can see for X? So in practice, what we do is something like this. What's the probability X is equal to 2? What's the probability X is equal to 10? Right? Well, we talked last class, and it was kind of vague, but we had probability mass functions. They were just kind of hidden. So we're looking back here, right? This essentially is our probability mass function. If we ask, plug in an X value to this function, it can spit out of us the probability of seeing that X value. It's just that we had no real functional form. It's not like it was A plus X or A plus B times X squared or anything like that. Now, that probability mass function for a binomial distribution actually has a functional form. So what it's going to look like is this. Right? So it's going to look pretty nasty at first, but if we break it down, hopefully it's not too bad. And see here, we're just looking at the difference between two variables, tracking something from one. Hopefully we're okay with raising numbers to powers on our calculator. This is going to be the part that probably looks a little bit foreign, and we have to figure out how to deal with this. Right? So does anyone know what a factorial is? That exclamation point in math? What would that, like 5 factorial would be what? Nobody knows? So if I have 5 factorial, what that's essentially saying is, and there's different ways of thinking about this, so if you've heard a different way, it's fine. But the easiest way to remember it is start with this number and multiply down to 1. It's supposed to be a 4 there. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2. So you can imagine these factorials get pretty large pretty quick, right? And this one what? 2 times 3 is 6. Times 4 is 24, times 5, or we get 120. It's pretty big, pretty quick. So it's going to present some challenges to us eventually, but for now, we just know that this is how we use these factorials. We should be okay. I would highly suggest, maybe even kind of as we're working on some of these, you should be looking for it, but definitely after class before we meet on Friday, because we're going to use this factorial on something else. Whatever calculator you're going to use, try to find the factorial button. So on most of them, it's like under some type of math or PRB, some probability button. Usually it's like you have to hit this button and there's some options. I know like in the TIA3 or it's like second math, and then you move over to probability, and then you've got a list of things you can choose, and one of them is this exclamation point. But if you're having difficulty finding it, let me know. I can try to help you. Honestly, most of the time it's going to be either physically, just like looking at the buttons, trying to find it, or Googling it if it's calculators that I haven't kind of seen. It's a little bit unique. Factorial? Yeah, so this exclamation point is just your factorial button. But for the most part today, we'll keep it somewhat simple with some values that, I can put 5 factorial, and even if I can't find the factorial button, because I know it's 5 times 4 times 3 times 2 times 1, I can enter that in my calculator. Won't give you anything like 30 factorial right early on, so that we don't have that button kind of in a hard place. So once we have this, all we need to do is identify the number of successes that we're interested in finding the probability of. That's our X. We need to find the probability of success on any one trial. Right? We're trying to find the probability of a number of successes. So the probability of any success on any one trial is going to be this underlying P. So like flipping a coin, that would be 0.5. The number of trials n is just the number of times we're going to run this trial. And then the factorial button we kind of already talked about. It actually has kind of this definition. We do n times n minus 1 times n minus 2, so on and so forth. All the way down to 1. A couple interesting things to point out at this point, or to point out here. And this is I actually watched a YouTube video on this the other day, trying to think about how to explain it. But it's some even I think the explanation is very math proof intensive and is very hard to follow. But for us, all we need to know is that some crazy smart mathematicians can prove that 0 factorial is equal to 1. Okay? So it's kind of like you can walk the logic and walk through the steps. It takes quite a few. But for us, let's just know that 0 factorial is 1. It's the same idea as y is 5 to the 0 power. What would this be equal to? If we had a math class where we talk about things with 0 power. Should just be 1, right? Now, the reasoning behind y isn't necessarily intuitive, and you can walk through the mathematical proof, and maybe it'll make sense to you, but these are the same idea, right? It's just kind of a rule of the mathematics that we can just use. We don't have to have a perfect understanding of why 0 factorial is 1 or why something raised to 0 power is 1, but we can use it. We can use it as a tool. So this will come in handy in different parts, or depending what the problem is. So let's just use a real basic setup, right? So let's say I've got this bias point, and when I flip it, right, the probability it comes up heads is 0.4. Okay? So my probability of success on any one coin flip is going to be 0.4. I then flip the coin what? Do I say how many times up there? 10 times. So my number of trials is 10. Right? I need one coin flip, the probability is 0.4, but I'm flipping it 10 times. I then might say, okay, what's the number of successes I'm interested in finding? So I want to find the probability that X, right, that 4 of them come up heads. So that's the probability that X is 4, right? Out of these 10 coin flips, what's the probability that I see? Now I'm just thinking about this, and this is kind of foreshadowing here. But if I flip a coin 10 times, the probability comes up heads and one flip is 0.4. On average, out of 10 flips, how many would I see come up heads? So if I have this biased coin, which is 0.4, I flip it 10 times, on average, I would expect 4, right? Yeah. So, this is kind of intuitive to us. Like if I was to look at flip a coin 100 times, if it was a regular coin, right, the probability of seeing a head is 0.5. If I flip a coin 100 times, the most common number of successes I'll see is 50 out of 100. But sometimes I would see 51, 48, right? Maybe even as high as 55. Like I can see different numbers of successes, right? It's not that I see 50 every single time, right? For any one small number of trials, I might see it kind of deviate from that expected value. So we're thinking about the expected value here. Of what you did in your head, the person that held up the 4 fingers, or whatever should be 4 here, that's kind of the most common number of successes, or the average number of successes, or my mean number of successes. You're just taking that number of trials and you multiply it by the probability of success in any one trial. That's kind of intuitively what you did, but this is like the mathematical formula. So here, 10 times 0.4 would give us that average number of successes is typically 4. So when we look for the probability of seeing exactly 4, it should be relatively high. Right? When I say relatively high, something quite a bit away from 0, right? A pretty strong likelihood we see 4. But to get the actual probability that we see 4 successes, we need to plug in our 3 components into that binomial probability function. So we look at it in the general form and start writing it out using our values, right? So 10 factorial over x factorial n minus x factorial, right? And I'm just writing in 10 for n and 4 for x. Probability of success to the x power, so 0.4 to the 4th, times 1 minus 0.4, the n minus x, so 1 minus 0.4 to the 10 minus. Just writing this out using my values. So, how can we make it a little bit easier? I would say you can kind of break this down into parts if you don't want to put this all in your calculator at once, if you're worried about like order of operation errors or not putting parentheses on something you need. You can kind of break it down into 3 components, right? And then you have 3 numbers that you just need to multiply each other by. So do the easy math first. That's also, I would say, like, even if you want to enter this all into your calculator, why keep all these parentheses? Like, I think in our heads we can see this is 0.6 to the 6th. Right? It's a lot easier to put in my calculator. So 0.4 to the 4th, write that number down. 0.6 to the 6th, write that number down. And then it's just a matter of figuring out what this is. Now, if you found your factorial button, you could do this pretty easily, right? But even if you didn't know where you're, can't find it yet, let's think about what we have up here. Right? So that's my numerator. Just 10 factorial, 10 multiplied down to 1. 4 factorial is there. And then this, 10 minus 4, is 6 factorial. Well, notice everything past this 6, I forgot my 4, is going to cancel. Everything below 6 there is going to cancel, and then I'm just left with 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. I have to enter that in my calculator, even if I don't know my factorial button is. So if I write these factorials out and kind of recognize what I can cancel, a lot of the times this makes it a lot easier. And I'll bring up a more extreme example here in a second of that. Any questions over anything I did up here? They changed the way this class is laid out. Next to the tables in the middle. Okay, I was going to say something doesn't look right. I forgot what it was. All right. So Any questions on that?
He said the same numbers on the top and the bottom, just cancel out.
Yeah, right, if I'm dividing 6 by 6, since everything's being multiplied here, right? Anything that I kind of see in the numerator and the denominator, it's the same, I can kind of cancel that out. And I guess technically I could have just canceled this part, and I would have more numbers to deal with, so. All right, so once I get these entered into my calculator, right, I'll get the probability of seeing 4 is about 0.25.
You might have gone over this, maybe I missed it, but the term you say flip a bias coin, what does that mean? What is it?
Oh, just that, you know, if we were talking about a regular coin, this would be 0.5, right? It probably comes up had this 0.5. I was assuming something different from here, so we had something other than 0.5. So you didn't think it's always got to be 0.5, right? Any probability of success. I think the next example we have will have something different. Yeah. So before we go to the next example, I want to try to jump the gun on an idea here. So we found the probability that out of 10 coin flips, that 4 of them come up heads with this biased coin, right, is 0.251. Okay. So that was that number of successes 4 was my mean, my expected value. So it should be the most likely outcome. Right? So really what I'm saying there, the fact that it's my most likely outcome, means that if I were to kind of draw out this bar graph, 4 should be the highest bar, right? The most likely outcome. Whatever your mean is, right? And kind of said here, we can intuitively think it's out of 10 coin flips, like most common response would be 4, 10 times 0.4 gives that 4. That means that I'm looking for the probability of 5 of those 10 heads. What has to be true about this probability relative to sin 4? Well, if this is the most likely outcome, that probability has to be lower. Right? And then it kind of intuitively makes sense, right? As I move to higher numbers of successes, well, what's the probability that I see 10 out of the 10 coin flips come up heads? Well, that probability is probably relatively small, right? But the idea is that as I move from that expected value or that mean, seeing these higher and higher number of successes just becomes less and less likely. If I think about a regular coin, where the probability of heads is just 0.5, and I flip it 100 times, the probability I see 60 of the 100 come up heads is a lot higher than I see 70 out of the 100 come up heads, which is higher than 80 out of 100, which is higher than 90. And then 100 out of 100, that's the least likely outcome, right? That's as far away as I can get from that expected value. And then the same thing would be true if we go in the other direction. Outcomes that are less than that mean number or that expected value, right? As we move kind of either to the left or to the right, those probabilities start to decline. Okay. So we'll exploit this a little bit kind of in some of the stuff we do here in just a second, but I wanted to introduce the idea now. We'll revisit it. So what if I had a different example where I know that if I'm selecting a person at random, the probability they have an undergraduate college degree is about 30%. At least that's what I'm told by the Wall Street Journal. Right? So the probability of any one person having a college degree is 0.3. I then ask 5 individuals, right? 5 adults, what's the probability that you have a college degree? And then I might be interested, okay, what's the probability that 3 of the 5 have a degree? Right? I'm trying to ensure that, maybe I have a sample I want to ensure that has a certain number of people represented as having a college degree. And so, the probabilities of 0 people starts to get high, then I'd be kind of concerned. But we'll just kind of use these, not use the value of 0 here. We're going to use the value of what's the probability that exactly 3 of those 5 have a college degree. So my underlying probability of success would be what? Probability that any one person has a degree, right? Or that we see a success in one trial. So we're told that's 30%, or the probability of 0.3. What's our number of trials here? I'm interested in whether or not if I ask an individual if they have a college degree, if they have one or they don't. And I go out and I ask 5 people, my number of trials is 5. And then the number of successes I want to find the probability of, well, my X would be 3. I would say probably that 3 of these 5 have a degree. From here, it's a matter of plugging these values, right? We've got N is 5, X is 3, the probability of success is 0.3. It's a matter of plugging them in my binomial formula, right? Once again, I kind of break this down into parts. I can do the easy math first. This is just 0.7 to the second power, right? Maybe take 0.3 to the third times 0.7 to the second, write that number down, and then figure out the factorials, right? But with these relatively small numbers, that shouldn't be too bad. Right? If I'm rewriting out that factorial, 5 factorial is just 5 times 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. And then 5 minus 3 is just 2. So 2 factorial would be 2 times 1. If we wanted to like cancel things, right, we could. And now I'm just left with 5 times 4 divided by 2 times 1. Or, right, 20 divided by 2 just ends up being 10. Right? So, writing out the factorial sometimes kind of helps us make it a little more sense of it, makes it a little bit easier, makes the numbers a little bit easier to deal with, unless we have really large factorials. Any questions on this? All right. So here, right, if I've got 5 individuals, the probability that any one of them has, or the probability that one of them has, sorry, the underlying probability that any one of them has a degree is 0.3. What would my expected number of people be out of 5 that have a college degree? Or what would my mean be, my expected value? If it was 10 people, and that probably was 0.3, what would kind of the mean number of people be that I could expect out of 10 to have a college degree? Ten people, probably, yeah, 3, right? What are, intuitively, I think we can do that in our heads, but really we're using this, right? So if I only have 5 people, right, my n is 5, my probability of success is 0.3, right? I can think about my mean would be 1.5. So this is a little bit tricky because this is a discrete random variable, so we can't actually see that value, right? But it is a weighted mean, right? And so what this is really saying is that 1 and 2 will be the most likely outcomes that we can see. If on average we would see 1.5, well, when we actually run the experiment, we're either going to see exactly 1 person have a degree or exactly 2 people have a degree. We can't see 1.5. So if you end up with a decimal, it's kind of the values on either side of it are the most likely outcomes. Right? So we can kind of think about what we're going to be looking at here. Something like this. Right, so my mean is 1.5, which means the outcomes of 1 and 2 will be the most likely. And then as I move outcomes further and further from that, the probability is going to decline. So I just found the probability it was equal to 3 was what? 0.13. So the probability that I see 4 people have a college degree, right, automatically I know that has to be, what range can I put that in? Yeah, it's got to be less than the probability of seeing 3 successes, because I'm moving further from that expected value, that mean. So I know that it has to be lower than 0.13. So if I'm looking at these values up here, I can answer this question right away. So if you've been paying any attention to me, I'm going to give you like 20 seconds here because we don't have to work through this one. I just explained to you a concept, a visual representation of that concept, that if we found the probability of 3 is 0.13, which of these has to be the probability that we see exactly 4 of the 5 have a college degree. Okay, so I'll give you a little bit of time just to get your iClickers out here, but then I'm going to close it pretty quick. Okay. All right. Everybody had a chance to get the response recorded. All right, 35 of us. All right, so if you were listening, what should this answer be? Yeah, right. Why is that the A? I literally just said and have a visual representation that as we move further from that mean of 1.5, the probability of those higher and higher numbers of successes are falling. Well, if we know the probability of seeing 3 successes is 0.13, we know the probability of seeing 4 has to be less than that. There is one value that is less than that, right? 0.028. So automatically, you know that has to be the answer without even working through the problem. Now, you can work through the problem. Like if we hadn't done this ahead of time, well, then all bets are off. I don't really know, right? But I also want to kind of think about why would an answer like D make no sense? So let's think about, I have this mean of 1.5, which I said is telling me that 1 and 2 will be the most likely outcomes that I see, right? So they're going to have the highest probability. Well, if the probability of seeing 4 was 0.8, it's impossible for 1 and 2 to be more likely because they have to add up to 1. The only thing left, there's only like 0.232 amount of probability left. So there's no way that we could have the probability of 1 and 2 being higher than the probability of 4 if that was the right answer, which so the answer doesn't make any sense, right? So right away, we should hopefully be able to rule out something like D. Okay? And then from there, it's a matter of plugging in our values, right? We've now got N is 5, X is 4, our probability of success is still 0.3. It's a matter of plugging that into our now, these things become a little bit easier. You can kind of imagine here, if I wrote this out, 5 times 4 times 3 times 2 times 1, 4 times 3, everything's going to cancel except for that 5. And then 1 factorial is just 1, so that's easy. And then we have 0.7 to the 1 power. Anything to the first power is just itself, so just 0.7. So, you know, we're dealing with things like the number of successes being really close to the highest number of possible successes, or really close to the lowest number of possible successes. A lot of times these formulas become a little bit easier to deal with, right? Because things start to become 0 and 1, you know, and 0 factorial is 1, right? 1 factorial is 1, anything to the 0 power is 1. So it makes some of the math a little bit easier, if we can recall this. Right? Any questions over, you know, like maybe if you weren't necessarily listening to me, maybe you don't understand why I didn't give you a lot of time to answer that, but the idea is I basically told you what the answer. I said it had to be less than 0.3, and then there was only one value less than 0.13. Okay. Any questions before we keep going? Yeah.
So on your graph you drew, you have 2 being a little higher than 1.
Yeah. So you don't really know which one's more likely. That just happened to be. It's easier to think about. Maybe they're equally likely, but maybe not, right? So we'll actually see some visual representations here where when we think about the outcome on either side, this mean for expected value is still influenced, right? If we think about it this way, I think I left off, there should be enough room here for a 0, but 0 is as low as we can see. There's more or fewer values on the left side than there are on the right. So the mean is going to be pulled up a little bit by these values, which means it's probably actually going to be that 1 is a little more likely than 2, but there's no reason that I'm going to expect you to know that. I just know that those are the 2 most likely. You don't know which one is more likely, but they are the 2 most likely. It's a good question. Just be more careful about how I draw my bars. Any other questions? So, this is what 0.028. All right, probability of seeing 4. So what's probably true about the probability of seeing 5? If going from 3 to 4, the probability fell from 0.13 to 0.028, what do you think is probably going to be true about the probability of we see 5 people out of 5? It's going to be really close to 0. I mean, it's going to be 0.0000 something. So with that in mind, this next one, what if I had not just the probability that X is equal to a specific number of successes, but that it's less than or equal to. So here I have it, or no, I have it at least here. So what's the probability X is greater than or equal to 3? So if we're not looking for one specific value, right? We've said all these are mutually exclusive. Like last week when we were talking about the outcomes for discrete random variables, they're mutually exclusive. I either see exactly 3 out of 5, I see exactly 4 out of 5, or I see all 5 out of 5. Right? I'm in one of those scenarios, and once I'm in one, I can't do the other. If there's only 4 people out of 5, then it isn't 3 out of 5, right? There's exactly 4. So whatever event we're looking at, think about this as maybe event A. I can just add up the probabilities of every possible outcome in that event because there's no intersection I have to worry about double counting. So here, what's the probability x is equal to 3? Plus the probability x is equal to 4, plus the probability x is equal to 5. Well, we already found these, right? So the only thing left to do is use x equal to 5, plug that into our binomial equation. Once we have that, we can just add those 3 up. So I plug 5 in as my x value here. I get about 0.002. So it wasn't quite as low maybe as I said earlier, but pretty close to 0, right? It's just a matter of adding those 3 up. We get our probability that x is greater than or equal to 3. Any questions on that process? Or I kind of explain it in a slightly different way. So it doesn't really save us a lot of work in this specific problem. But if this is event A, I know that I can find the probability of A by taking 1 and subtracting the probability of its complement. And that was kind of our complement rule that we had. So if A is that x is greater than or equal to 3, a complement would just be x is, less than 3. But being less than 3, what's the first possible outcome I could see that fits that criteria? This is a discrete random variable, so first outcome that would fit this criteria would be x is equal to 2, right? That's the first number that's less than 3 if I'm dealing with something that's discrete, right? I can only see the integers. So another way of thinking about this is, what are all the possible outcomes that fit this criteria? Well, x could be equal to 2, x could be equal to 1, or x could be equal to 0, right? So if I add these 3 probabilities up and then subtract them from 1, I could have also found the probability that x is greater than 3. Now, I still have to use that binomial distribution function 3 times, so it didn't really save me a lot of work. But you can imagine a scenario. Let's say, I want to end up with a really high n. So let's say I've got my n is 100. My probability of success is like 0.95. And I'm interested in what's the probability that I see 90. Actually, scratch that. What's the probability that x is greater than or equal to, we'll use 97. And actually, is that what I want to do here? No, I want to prove a better point. Let's do the probability x is less than or equal to 97. I think this will really show the power of it instead. So this could be something like that's really a high likelihood of occurring, right? I don't know, maybe it's like a probability that someone doesn't have it hasn't served jail time or something. Maybe hopefully it's that high. Right? And then we've got 100 different individuals we're looking at. What's the probability that 97 or fewer of them, right, out of these 100, didn't serve jail time or whatever this, value x is, whatever this variable x is. When I start to write this out and I think about, okay, if this is my event A, everything that's in that event, I could find the probability of every outcome and add them all up, right? So the probability x is equal to 97. What's the probability x is equal to 96? What's the probability x is equal to 95? All the way down to 0, using that binomial function, 98 times? That doesn't seem like I want to do that, right? It's not something I would ask you to do on the exam. But I could have a example of something similar to this, because you know that the probability of any event is equal to 1 minus its complement. But what would the complement of A be here? That x is greater than 97. What are all the outcomes here that fit this criteria? Well, X could be 98. Probability X is 99. And the probability, I'll get out of the way here in a second. And the probability X is 100, right? Well, now it's very possible for me to find this, right? I can plug in 98, 99, and 100, right? So I can use that binomial distribution 3 times, find these probabilities, and then subtract them from 1. Whereas before, I would have had to use that binomial distribution function like 98 times, right? So using this complement rule can make things that weren't really possible before actually seem possible. Any questions on this? It's a little bit sloppy, but right. Probably X is equal to 98, probably X is equal to 99, probably X is equal to 100. So let's say I want to find this 98 probability. So I start to plug things in. N factorial divided by X factorial and minus X factorial, probability of success to the X power 1 minus the probability of success to the N minus X. So I can probably get this part into my calculator okay. But if any of you have found that factorial button, what happens if you try to put 100 factorial into your calculator? Did anyone find it earlier? Yeah, right. It can't do it. It gets mad at you. So this is a good example of, tools are great, right? Computers, everything make our life easier. But a lot of times, the computer doesn't quite yet have the complexities of the human mind, right? So it can't recognize, it only can live within its construct. And so it looks at that and says, well, I can't do 100 factorial, right? But if you as a human look at this and you say, well, look, I know that 100 factorial would just look something like this, right? All the way down to 1. 100 minus 98 is just 2. So 2 factorial, that one's easy enough. And then 98 factorial is just 98 times 97 times 96, all the way down to 1. Well, notice everything past, actually, 98 is going to cancel, right? So that we're just going to be left with 2 times 1 and 100 times 99. Right? So if I just kind of write out the first few numbers of those factorials, a lot of times I'll see, oh man, a lot of things are going to cancel here. I can actually do this by hand. I can enter this into my calculator and it for sure can handle, right? A dollar store calculator can handle this. Right? So this is one of those situations where sometimes being a human is actually better than just the machinery in front of you. So it's good to know how to use these tools, but if you don't understand the concepts behind what you're doing, you might say, well, we just can't do that. We're stuck. We're stuck in the calculation for this, I don't know, new rocket that we're going to take. Elon Musk took this approach, right? I'm just going to give up, right? The computer says I can't do it. Well, no, let's think about what we're trying to do, and it might actually be a lot easier than the way that we're just entering it into our calculator. I was making a great philosophical point here, but no. So like this is, sometimes we'll run into this where it looks like this is crazy, right? How can I do this? Well, if I use the complement rule, it makes it a little bit easier. And then I start to try to find this probability. Well, my calculator can't do this. Well, let's rewrite it. Oh, we can make this a little bit easier. All right, so those are some of the kind of tricks of approaching some of these problems that may seem on their face like we couldn't solve them, but we actually can. Okay. Yeah.
What are you doing about 95 and then 95?
Say that again.
What are you doing about 0.95?
0.95.
After the.
Oh, yeah, so obviously you would find this number and then start to multiply, like, you're saying like, how would I find this? So you
My
should just
calculator gives me overflow error.
0.95 to the 98. You have to you can get a computer or something that has a little more power. I think I kind of chose an extreme example to make this point, but yeah, I guess there is going to be a limit that we would hit in terms of the number of successes. So I don't know exactly where that would be. I know I think for T83 for the factorial it's somewhere in the 60s. I don't know You know, it depends on what calculator you have, what you would hit kind of overflow that. But I'm not going to give you, if I gave you one like this on the exam, it would just be something where probably more like smaller numbers, but you have to use that complement. I just wanted to make the point that like, just because we get these overflow errors, we could simplify things. Now, if you get an overflow error with your powers, well, now we got a little bit of a problem, but right, this is going to be so dramatically close to, I mean, one that's probably the issue is it can't take it out to a certain decimal. But we'll eventually see. I don't think we'll get there today, definitely won't. Just got 5 minutes left. But I'll kind of show you how we can do this in Excel as well. On the exam, I'll give you much smaller numbers, but I still might do something like, what's the probability X is less or equal to 19 out of 20 trials, which taking the exam, you can't use that binomial function 19 times. You might have to use that complement. Any other questions? All right, so we'll save this for next class, kind of revisit that idea, but I wanted to go back to this example to end class because I think it's kind of interesting. And we can use things that we've already talked about. So taking a little bit of a step back, instead of thinking about a binomial distribution, let's just think about if we had independent events. So independent events told us that if we wanted to find the probability of the intersection, that if they are independent, I should just be able to multiply the probability of each event. We have this set up like in a classroom like this, and I think I assume 40 people. What's the probability that 2 of you have the same birthday? Right? We're born on the same day. So a lot of times you ask people these questions, or we assume that there's no twins. Nobody's parents were like trying to plan to have a kid around the same time, right? Every birth is independent. Okay. So most people would respond kind of that they think this probability is relatively low. Right? We can actually use what we know to calculate this. It might be a little bit counterintuitive. So, all right, then how many people would you need to break past this point of 0.5? You can imagine, a room of 100 is a lot more likely 2 people have the same birthday than a room of 10. So what's that kind of number that kind of crosses over that probability of 0.5? If we instead think about, okay, what's the probability that X is that that somebody has, at least 2 people have the same birthday? Well, if we rewrite that as kind of 1 minus its complement, or, right, 1 minus the probability that nobody has the same birthday. We can actually find the probability that nobody has the same birthday. We think about kind of if I went through and started asking one at a time what your birthday was. So let's say, start with you, say, okay, what day were you born? The probability that he has a unique birthday relative to everyone I've asked will be the first person I've asked, right? So I mean, probability is 1, right? You have a unique birthday because I've not asked anybody else about their birthday, right? So we have this probability of 1. And I go down, what's the probability the next person has a new birthday? Well, I only have 1 recorded birthday. So there's 364 other days left. So 364 out of 365. And the next person, 363 days are left. So 363 out of 365. I can then go through and do that for every single person. I have the probability that every person I ask has a unique birthday, which is really a different way of saying probably that no one had the same birthday. So you can actually go ahead and do this for independent events. You just multiply them all together. You actually end up with 0.109, but remember that's the complement. So you still need to subtract it from 1. So the probability in a room of 40 that somebody has the same birthday is almost 90%. So pretty counterintuitive. In fact, I think if we actually work out, it's 23 people you need in order for it to go over 50%. So if you're in a room of more than 23 people, you should always take the bet that at least 2 people in the room have the same birthday. Okay? So we'll do a little more with binomial, then kind of move on to the Poisson. Don't forget there's going to be that additional YouTube video I expect you to watch before Friday. We'll probably ask you a few iClicker questions related to it. Okay? All right, I'll see you guys on Friday.